In this video, I'm going to discuss how the Antarctic ozone hole forms and how volcanic eruptions can impact ozone levels. Then we'll be doing a short case study on the Mount Pinatubo eruption to see the impacts it might have had on the ozone hole in the subsequent years. Around the months of September and October, a localized region of ozone depletion is apparent in the lower stratosphere of the Antarctic. In the late 70s and early 80s, scientists discovered this phenomena that was proven to be exacerbated by anthropogenic sources of chlorine gas in the form of chlorofluorocarbons, or CFCs, found in hairspray bottles and shaving cream cans. The worsening of this low ozone region, which threatened their protection from UVB rays, caused a global scare and urged the signing of the Montreal Protocol in 1987, cutting the use of CFCs globally. But what exactly causes this hole to form? In the months of May and July, the Antarctic experiences its winter season. Temperatures of less than -77 degrees Celsius aid in the formation of polar stratospheric clouds that are largely composed of nitric acid trihydrate, or NAT. The particle surfaces of these clouds provide a domain upon which heterogeneous reactions can occur. 99% of chlorine is usually in the form of reservoir species, hydrochloric acid, or chlorine nitrate. So with the presence of NAT, these species can convert to Cl2, which will go on to produce ozone-destroying chlorine radicals. Most of the nitric acid from the NAT will then settle out in a process called denitrification. The abundance of Cl2 formed during the wintertime will begin to photolize as spring approaches. This process forms Cl radicals, which go on to catalyze ozone loss cycles. Additionally, since nitrogen oxides are mostly settled out, chlorine is not getting converted to its reservoir species as usual, allowing for elevated levels of chlorine ozone depletion. This is illustrated by the diagram. Only when the polar vortex breaks up are nitrogen oxides able to mix in, causing chlorine and bromine to convert back to reservoir species. That's when the ozone hole starts to fade away. It is understood that volcanic eruptions send large amounts of sulfate aerosols into the air that eventually reach the stratosphere. These particles again allow for heterogeneous chemistry to occur. Nitrogen oxides can be converted to the reservoir species N2O5 during the nighttime, but typically photolize quickly back into nitrogen oxides in the daytime and go on to send chlorine radicals into their reservoir species. However, with the addition of sulfate aerosols, N2O5 also hydrolyzes into nitric acid, which is an even longer-lived reservoir species. Thus, a volcanic eruption will contribute to the excess levels of ozone-depleting chlorine, which isn't being actively converted to its reservoir species. To investigate the impacts of a volcanic eruption on the Antarctic ozone hole, a case study on Mount Pinatubo was conducted. Mount Pinatubo, an active volcano located in the Zambales Mountains of the Philippines, experienced one of the largest volcanic eruptions of the century in 1991. Scientists state that this eruption produced the largest stratospheric SO2 cloud ever observed by modern instruments. If we assume that there were around the same amount of polar stratospheric clouds in the years pre and post Mount Pinatubo, we might expect that the addition of the sulfate aerosols caused increased ozone-depleting halogen concentrations and a decrease in average ozone concentration in the ozone hole after the eruption. A study published in 1993 tracked chlorine dioxide abundances in the late fall of 1991 and 1992 in Antarctica. The presence of chlorine dioxide was an indicator of enhanced chlorine radical chemistry, which could indicate heightened ozone depletion in the year after Pinatubo's eruption. If we focus on the bottom image, chlorine abundances in the fall of 1991, before Pinatubo marked by the X's and crosses, were much lower than the abundances in the fall of 1992. The solid line was a diurnal model calculation that assumed 30% of chlorine residing in reservoir species had been released. Because this line aligns closely to the data post Mount Pinatubo's eruption, it can be concluded that there were heightened levels of chlorine radical chemistry in 1992. Since we assumed earlier that the number of polar stratospheric clouds likely didn't vary much between 91 and 92, we would expect ozone levels to decrease significantly in the years after 1991. Data was acquired from the NASA Ozone Watch program that quantified the minimum of the mean ozone for multiple years, between September 21st to October 16th. You can see from 1991 to 1994 that the minimum mean ozone experienced a significant decrease of about 27 Dobson units, The value in 1994 would be on record as the lowest mean ozone value from 1979 to the present. These images taken by NASA Ozone Watch show the average ozone hole size from 1990 before Pinatubo's eruption to 1994. The purple-blue colors represent the lower range of ozone concentration, and the oranges and reds represent higher concentrations. The image from 1994 shows quite a bit brighter purple region near the center of the hole than the image from 1990, illustrating a reduction in ozone within the region defined as the Antarctic ozone hole. Data collected by NASA proves a reduction in ozone in the few years following the eruption of Mount Pinatubo. Whether this was a direct consequence of the sulfate aerosol addition to the stratosphere is difficult to prove, but the enhanced levels of chlorine dioxide indicate that there was an unusual decrease in chlorine reservoir species in 1992, which likely played a role in the significant reduction in observed ozone. So there you go. We were able to explain the formation of the ozone hole and how ozone depletion is exacerbated by volcanic eruptions. Our case study on Mount Pinatubo gave us a glimpse of how these two phenomena can interact. Hope you enjoyed the video.